So good morning, everyone. So I'm Weisong. So I'm from Hong Kong Poly. So okay, so great pleasure to host this year. So morning, Kousik. So for this year, it's first workshop on the intelligent vehicles mixed urban. So specifically, we focus on the safety and certifiability for navigation and control for the IV for intelligent vehicles in complex urban scenarios. So for this year, so the supporters, in terms of the partners, including PolyU and quite a few universities, including the DRR and Siemens is industry partners, and also including BOA, Shandong University, and UM. So in terms of organizers, so I'm from PolyU and Dr. Daniel from Dia from DRR, and the team from Siemens, and Dr. Zhang from BOA, and the person Wang from Shandong University, and also several members from PolyU as well, and also Dr. Zhang Haoming from TUM. Dr. Bai from PolyU as well. So for today's workshop, in terms of the things and discuss topics, including the first thing is about the fast and cost-effective sensor fusion localization. So this is going to be about the navigations. So the second thing is about the AI-driven safety, certification, and resilience. So for example, we are going to answer some questions about how can AI method be used in estimation while ensuring the interpretability and fail-safe behaviors. So our speakers, including the first speaker is going to be Prof. Shi. So Prof. Shi is associate professor from Hong Kong PolyU. So Prof. Shi is going to give us a talk on the GNSS RTK and INC integration for the post-processing applications. So it's going to be roughly around like 20 minutes for presentations and 10 minutes for QA. And the second talk is going to be Prof. Timothy Barfoot from UT. So it's going to be talking about the radar. So also I personally have read a lot of papers from also the books from Timothy Barfoot. Okay, so the third speaker is going to be Zhang Fu. So Zhang is at least to me is quite an expert in the field of LiDAR and also the UAVs. So today the topic is going to be the efficient and robust LiDAR-centric localization for the drones. Also recently, Professor Zhang have published quite a few papers on the science robotics and TROs. It's really a great job, especially in the LiDAR and drones. So after this talk, we are going to have a short break for around 30 minutes. We can enjoy some refreshments. So later on is going to be Zhou. Zhou is an expert in the field of event cameras. So like a lot of SVO and event camera based localization. So today the topic is going to be advancing autonomous vehicles with neuromorphic event-based vision. So Zhou is also very expert. Also personally, I just say I read a lot of papers from Zhou as well. So the next day is going to be Dr. Shan The topic is going to be implementing a connected and automatic vehicle track in the Australian urban traffic. So the key learnings, very interesting sharings. Actually, in Hong Kong PolyU, we also do lots of similar stuff like the connected and automatic vehicles. Also, we say like intelligent vehicles. So last talk is going to be for Shreyas. Enabling for safety and performance of difficult dynamics. And later on we are going to have an open discussion, and I am very sorry and now cannot be there because of some personal issues. I cannot be there. So we have a strong team like Darren and Yixin is going to be there to support this workshop, and of course we have speakers to be there to support this workshop. And also in here is a workshop site. So in here is a quick advertisement. So actually we also post our workshop to this ITS societies, and simultaneously we also have a ITS committee on the topics of navigation for the IV. So this is Shreyas, and also Daniel is also the organizer of this workshop, and this is me, and also we have advisor Dr. Shi. So here is a QR code. So let's see later how we can contribute to this technical committee in the future times. So the goal is to establish a hub for advancing research in specifically for navigation related topics for IV. So again, I want to show my great appreciation for like mighty speakers and organizers attending this workshop, and I wish we have a great success for this workshop. Yeah. So Darren, Yixin, I think I will pass the time to you to host the rest of the talk. Okay, thank you.
Okay, thank you. Thank you, Professor Weisong, and thank you, Darren, for inviting me to give the talk. It's really an honor and pleasure to share our insight on GNSS RTK and INS integrated systems. So I prepare roughly 25 minutes, but I will control myself to make it a bit quicker because I just know it's 20 minutes. So let's see how it goes. Right. So I'm Lita. So welcome everyone to this workshop. So let's get started. So give me 1 second. Okay. Good. Okay. So, because I'm the first speaker, so let's talk about a bit the market driver for GNSS. So, according to the US market report, GNSS market report 2024, actually, this is we have a roughly 4.6 trillion euro that's going to accumulate between 2023 and 2033. And if you look at the portions for the raw automotive, it's roughly 26% of the whole market. So that's big. And not only the raw automations, but also like agriculture, rail, and drone. For me, these are the UAS system. So I believe that GNSS still play a very important part for this unmanned autonomous system, especially on the road traffic. Right. So for me, I'm looking at the market need. This is what I can find. I think they're very strong and the need is very strong and require urgent GNSS RTK technology. The first one, interestingly enough, is robotic mower. So this is basically a grass cutting machine that running around in the golf field or in your backyard. And this is actually a lot of people want it. And for these solutions, it require low cost GNSS RTK. Basically, it's like $1 chip, but with very cheap INS and odometer. And it require real-time operation. So for me, this is a very difficult challenge because everything's cheap and it requires to be done in real time. So if we can really have this solution, you're gonna see a lot of this robot running around. And the second application for me is that the HD mapping by the mobile mapping systems. So in these applications, we can using a better receiver, like commercial receiver, $30 receiver, and you can have a lot of RTK corrections, and you can have better INS as well. And what is good for me is that this can be done post-processing. So much easier in my perspective. So I got to work on this before we looking at the real-time solution. So this is going to be our key application of the day. Right. So for this level 4 autonomous driving navigation, so we require HD map. Usually you have a machine like this, a beautiful monster. You have a all set of different sensors, especially like LiDAR, that are being used for making the point cloud map. So we believe that even in urban Kenya, this is one test I done with Professor Wen back to 2022, is that we're using long, a very famous pipeline from CMU, and we're using long at a high constraint. We can easily achieve 30 centimeter absolute accuracy after a loop closure using the LiDAR point cloud. So for us, you get a local accuracy, 30 centimeter, dense urban like Hong Kong, crazy, a lot of bus running around, still quite okay. So it's not that really that challenges. But what is really interesting is that when you're looking at a Hong Kong mobile mapping system, of course, they rely on the pipeline of LiDAR and visual lens, and they tightly integrate LiDAR and visual lens with INS. This is tightly coupled solutions. But they're using GNSS RTK as a loosely coupled solutions to integrate with the tightly coupled pipeline of the visual lens and LiDAR lens. So GNSS is still quite important, but why? Why is it important? So let's look at this. For us, this is trying to connect in the maps. So we have one Mother Earth over here. And if you have a local HD map, like let's say if you survey in San Francisco, you survey Mountain View, you survey in San Jose, you have all this local map, but you need to really run in a this service together. You need to attach all this map together. You need GNSS that is really looking from far from inside, from outside, and putting this map into a global unified data systems. So that's where GNSS come into play. And if we can have the RTK solution, which is centimeter level, and it's going to be good. And this can allow us not only to make the map ourselves, you can also working with other map provider to run your autonomous driving service along the globe. So this is really a scalable solution if you can have GNSS as part of your HD map. So how do I know this? Actually, I was in sabbatical leave in the last 2 years at Google Android team. So I'm working closely with Google Map and Android Auto as my client, and I give suggestions to Waymo and Wings. So in all these product areas, they really believe that GNSS is part of their important solution, so that they can achieve this global scale level of applications. So land level, decimeter level, centimeter level GNSS solutions are still required in a lot of road traffic. So that's what I'll emphasize why I have to talk about GNSS in this IV instead of just using LiDAR and visual. Right, so that's enough of the background. So let's looking at what is the existing solutions for generating that loosely coupled solutions for GNSS to integrate with the tightly coupled pipeline. So people using some very expensive stuff like Novatel spend CPT. So basically, it's a fiber optics gyroscope with expensive antenna and receiver. It are together. They put it into, excuse me, they put it into one very expensive software. It's called Inertial Explorer as well to provide the solutions. But what is more scalable solution that really can let everyone generating the HD map using much cheaper one is we are looking at using just the U blocks, a $30 level of chip, and with maybe okay you can pay $100 you've got the potential. If you got a patch antenna again like this is a $20 or you can get $100. So we want more scalable solution. You using something like this. And people are in robotics field has been using this RTK lib as an open software pipeline to get you an RTK solution. This is what we have today, but this is obviously not good enough. So our goal is the goal in our team is that to develop a low cost options that is compatible with different GNSS module and IMU, which is low cost. To achieve this, actually, we have 3 research questions we need to address. What filter or optimizer we need to use? Should we using just a RTS smoother or just or an FGO? The second question is, how do we know the quality of the GNSS solutions and measurements? And the third question is, which GNSS solutions are credible? I will talk about this credibility a bit more later, so because it's a new term that we've been used. Right, starting with the first one. So for the filters and optimizer, which one should we use? So back to 2021, so Professor Wen and I actually, and also Tin, who and Xiwei, we are actually the organizer of this workshop. We have one very popular paper in GNSS field is to looking at how FGO is useful for GNSS INS integrations. So at that time, we come up with the conclusion is that okay, both of them using Gaussian, but for FGO because you got a numerical solver, so the Gaussian assumption is not as strong. And EKF using first order Markov chain and FGO using the epochwise nonlinear optimizers. So the cons, FGO very expensive. The pros is that it's more robust when the 2 assumptions are violated. So this paper is go really good in the field. And if you're looking at the publications of both common filter and FGO in terms of GNSS INS integration, from 1985, which is the year I was being generated to the world, which is I was born, and to 2025, 40 years of time spent. This is the term. So we're looking at only Scopus, okay? Scopus. This is the paper they published using common filter in GNSS INS integrations with all these keyword search conditions. You can see it's keep going up crazily like common filter. That means navigation has been still really popular for today. But since the 2012, when the paper from Chimas was published, the first paper using FGO in GNSS, you can see it's going crazy in recent years as well. And with that, actually, when I come into IO and GNSS Plus, we have hearing a lot of things people discussing. So, oh, this FGO is coming out. Is it really better than EKF? And a lot of experts asking the question is like, okay, I think EKF can do what FGO does. It's nothing fancy. It's just a numerical solver. So we're trying to address these questions like what's their relationship? Are they really just what we discussed in 2022? So coming back to that, so we're coming out with a new paper, which is called FGO Meets Faster. This is just released in the last month. You can find in archive. So we're trying to derive from KF to FGO. So starting with in the linear system, so common filter is a linear system. If you relax linearity, become extended. If you do epochwise iteration, then you have EKF. If you do robust, then you can have the analytical model of the robust function and put it in EKF. You can have REKF. You can combine both of them together, become REKF. And then you formulate into FGO, it becomes a recursive FGO. That's the term we use it. And then if you even relax the first order of Markov chain, it becomes a sliding window FGO. So what we're showing a simulation result to talk about all this detail. So one simulation is we have a TOA engine and with a circle motion, this is simple simulations. And then we have a G for Gaussian, Li for linear because the beacon is quite far away. NG, non-Gaussian, we're using Gaussian mixture model. NL, a nonlinear beacon is actually much closer. So if you're looking at this EKF and in the linear and Gaussian result, everything is pretty good. Even if our initial point is quite far away from ground truth, everything is good. What if we have nonlinear here? So because you take the first order Markov chain recursive nature, it takes a few epochs to coming back to the solutions. If you put linear but it's non-Gaussian, then you see your solution is within noise, so the solution is not as perfect. If you combine non-Gaussian and nonlinear for this EKF, you can see your solution taking a few seconds to converge and still got some noise after. What if we taking into iteration, epoch-wise iteration into consideration, this epoch-wise? So we have EKF over here for the nonlinear. You see, even our initial point is quite far away. It quickly converge because you do the epoch-wise iterations. So it converge over here. But this doesn't really help him when you have non-Gaussian problem because it's converging to the non-Gaussian areas. So what can we do with robust? If we have a robust estimator, what happened to non-linear is interesting is that after you adding in the robust functions, you increasing non-linearity of your model. So even in everything is linear, you're already taking one more epoch to converge to the solutions. So you see, when it is even more nonlinear, it takes even longer time to converge. But when you have just non-Gaussian noise, this outlier is not really a problem for robust. So you add everything together, taking time because you add in robust and nonlinear, taking more time to converge, but the noise doesn't really have too much impact. So you can imagine if we put two robust and the iteration all together, they are pretty good. And for us, this solution, robust iteration EKF, is actually what we call a recursive FGO. So that's where people said what FGO can achieve, EKF can achieve too. Just achieve analytically. Just achieve. So it's much more computational light. Right. But what is different is recursive FGO and sliding window FGO. So if you're looking at this result, so we have one epoch recursive FGO and sliding window FGO. So their differences is that for the recursive FGO, so their state is initialized by the propagation. But for sliding window FGO, their state is initialized by the value you are given into. So usually using weighted square or the other solution to initialize it. So that's the key differences. In looking at just one window size, one epoch, you can see sliding window doesn't really do better than recursive. But when your epoch size increase, you can see the CP95 deduct quite greatly. So this is the conclusion we have back to the paper 4 years ago. So we still believe sliding window is better than recursive FGO, is better than the common filter in many ways. But the real question is, how about the RTS smoother batch and batch FGO comparison? So for those of you who are not familiar with RTS smoother, is that common filter is a forward solutions. RTS smoother is combining the forward solution and backward solution and combining both of them together. Very similar to FGO, but it's epoch-wise recursive, combine everything together. So for this, we're still doing analysis. So our student Baoshan and Zhang is working on that. Hopefully next year we can provide you more insight on this one. So for this stage, we'll stick with FGO for our application at this stage. Right, that's the first questions we answered. The second question we ask ourselves, how do we know the GNSS solution and measurement qualities? So if you look at a GNSS pseudo-range measurement error budget, from satellite to receiver, there are a lot of delay. If you consider all this delay here in the measurement model over here, and you can really kind of like trying to eliminate length, you still have the noise. So this noise add up together. We believe they are zero mean Gaussian noise. They add up together. They are still Gaussian. If everything's still Gaussian, using weighted square, using common filter, your covariance is actually quite okay. But for urban area, so I love about the topic. This is where our topic today. You have multipath and you have unloss. And we know at these areas you have a positioning error much bigger, 50 meter. And if you're trying to separate a loss and unloss using some key performance indicator like carrier to noise ratio and elevation angle, it doesn't really separate what is LiDAR sign, what is non-LiDAR sign. So that's the real challenges. If you are lucky enough, you have 3D beauty model to play with, then you probably can generate something like this, a sky mask, and you can extract a new indicator that is the delta elevation angle between the building boundary and the satellite. And using that as a key indicator, you probably can come up with a new weighting scheme that is fit into the measurement arrow. But we don't have that in general, right? So 3D building model is quite expensive and it's not globally available. So the question for us is like, okay, that's using AI to dealing with this. So I think this is roughly 7 years ago. I was invited to write this article to talk about how AI and machine learning can help in GNSS positioning. So of course, we believe that the AI is basically trying to model based on data, right? So the use in the phenomena we don't know how to model, and with a high complexity and time variant and nonlinearity things. So that's where we're going to do. If we're looking at from a GNSS receiver perspective, that with incoming signals, incoming to antennas and measurement engines, positioning engine, then you got position solutions where AI can do a job on this. So for measurement engine, you can do in the correlator one, you can invent some of the new discriminator based on AI. That's about 11%. Or you can do the pseudo range corrections, about 18% of research, or you do loss and loss classification, about 56% of paper doing this. Or you can do position classification or even position corrections. That's about 14% of the paper. Today we talk about if we can do position classification, what does it help to our problem, to our application, GNSS INS integrations. So let's look at this pipeline that we developed and we published last year in Plains. We have RTK, we have a pre-integrations, then we're using a GCLib FGO, which is a SOTA open source code for GNSS INS integration. For those of you who haven't downloaded it, go ahead and try. This is one of the best open source code that we ever tried from Shanghai Zhou from Dr. Chi. So we're using this coming out with the real-time solution first. Then we change this GCLib into a batch solutions. After we have the batch solutions, we develop an unhealthy GNSS epoch classifier that's actually saying that, okay, so when your position error predicting larger than 2 meters, then it's unhealthy. Then we're using this solution as initial guess and this unhealthy epoch to adjust their covariance. Then we have a second layer of batch GC FGO. Then we got finalized state. So this is our suggest pipeline. So in this pipeline, we're using the data for UrbanNav, for those of you who maybe tried, and also the Pi RTK. And the antenna we are using, a patch antenna, receiver using F9P, and we're using dual frequency, a multi-constellation, and this is our mask. And this is our ground truth provider, the expensive Novatel. Right. And for the method we benchmarking is that we have a naive solution from U-Blocks. And we have the IE, which is the inertial explorer, but we changed the receiver from FGO, from Novatel to F9P. And then we have a bunch of different FGO pipeline, real-time pipeline from GC, the batch GC, and also the second layer batch GC, which is what we propose. This is the benchmark we've been discussing. So I'm going to show you one result in UrbanNav Deep. So this is the positioning arrow. This is time. This is arrow. Different color for different method. So for IE, you can see the solutions doesn't really close to good because this IE Explorer is designed for Novatel receiver. When you put in U-Blocks, it doesn't really work that well. And for U-Block solution, you can see roughly mean is 3 meters and 95 is about 4 meters. Real-time GC. In real-time GC, you see the 95 is going up crazily in some of the period. Batch, it reduced a little bit, but second layer batch, it reduced quite crazily. And this is our solution. If you look at the solution, the blue one is actually going quite close to the ground truth running on the road, while the other solution might drift away at some times. So we are quite proud of this solution. But how does this achieve? So we're looking at only 3 solutions, real-time GC and batch GC and second layer GC. Because this batch GC provide initial solution for our second layer batch. So this is actually the performance. This is positioning arrow, all right? So what we do on the classifier is that we classify each of the epoch with different color meaning like when we're trying to do the classification, if we believe the solution is normal, it's blue. And if we believe that the solution is bad, it's green. So you can see in this area, they are coming to really bad. We know it's not good. So that's how our solution batch, that's how our solution, the batch result is reducing this part quite crazily, like from 95, from 21 to 2 meters. That's how it works. And we also test in different scenarios, like in harsh, in deep, in middle, in suburban. Their solutions all are quite stable. Only this harsh doesn't really do too good, but we're still quite optimistic on these solutions. Right. But this is only looking at one solutions using GNSS solutions. But this is our FGO, the overall pie chart. So we want to look a bit more. How can we really in this FGO in FGO graph chart? How can we looking at this the noise covariance? We want to learn better using the data instead of just a classifier. We want to learn. Can we using AI to determine this noise covariance matrix? That's what we want to do over here. We want to learn this noise covariance using AI. So why we believe this is doable? Google is very nice. They released their data. Like there's a Google smartphone decimeter challenges a few years ago. They're 3 years in context. They provide a lot of trace and put in this competition in cargo. So that means we now can try a lot of data and doing machine learning approach. So what we do is that when we have an FGO, can we use a neural network to turn in a weighting based on the data? This is what we propose. We are implementing differential FGO for weighting adoptions. And in this research, we won the best presentation award in 2023 GNSS Plus. So we adopt this differential FGO from Dr. Pineda, from their famous library thesis. Yes, and this is what it looked like. So when we have a cost functions, this is our cost functions of FGO, and this part is our covariance. And this covariance now is trained by a neural network. And this neural network, these are the parameters that to be trained, right? So we put theta over here. So after we use a neural network, we train the covariance and put into the vector graph. We have the estimated state, and we have ground truth, we have the loss functions, and the gradient of the solution, the gradient of this neural parameter can be achieved and putting a closed loop. So this is how we implement the FGO into adapting the weightings. So we're trying this in the Google smartphone decimeter challenge data. So 61 for training and 85 for testing. You see, the device using is Pixel, but we're also testing on something like Xiaomi and Galaxy phone at different location as well. Right, let's looking at the result. So this result, we excluding Samsung phone and Xiaomi phone, looking at only Pixel phone. So a different line here means a different weighting scheme. And this is a CDF. So that means error, and this is probability. So if we put all the cost function in the same weighting, this is roughly 1. And if we put uncertainty that report by the device, this is like this. But if we using our DFGO with a different activation functions, you can see the performance is greatly improved comparing to the device report uncertainties. What is even more interesting is that after we testing all data, we realize if we're using device uncertainty, the solution is even bad. So that means for Samsung and Xiaomi, their device solution are not trustworthy, but our solution doesn't really affect it by that. That means our solution, the FGO, can figure this out when working at the different GNSS module. That we're really proud. What is even more interesting is that we were presenting our paper. There's the other team coming from Canada. They're finding out, okay, so there's a weighting ratio between pseudo range and the carrier phase. They put in the weighting ratio at different value from 100 to 600. They manually test which one is the best. So this is time. This is the positioning error. So based on their heuristic determination, they determine the weighting between pseudo range and carrier phase, putting 100 is the best. But our DFGO finding this out by data. So this is our weighting between GPS L1, pseudo range, and the carrier L1. So we also making this 100 time differences. So that means our data can dig out this 100 times the heuristic done by human as well. So that is what we believe, that when you have more data, then maybe using this data-driven approach to determine weighting is really good idea. That's what we're really proud. Now coming to the third questions, is also a new research we have been working with. So now we're talking about GNSS analysis integration. So we have a lot of different pipeline. We have the FGO, FGO, people using weighted square, people using RTK lead. So which one is the best for the integrations? Let's say in the loosely coupled GNSS analysis integration case, which GPS solution is the one that we should trust for integration? What do I mean? If you have a two GPS SPP estimation, you have two like this. This is your ground truth. You have one solution that giving you the red circle, which is estimation result is over here, but your uncertainty is this one. And you have the other one is giving you the solutions with also at the same position start here, but with blue one. Which one should we use? Which solutions should we adopt into this GNSS INS integrations? In the mathematical derivation, descriptions. So you see, if in this two FGO GNSS INS integration, which solution should I use? Red one or blue one? So we have to define a metric to determine which one to believe. We believe that is called credibility. So we check in the paper online. So one of the most popular is called NESS, which is normalized estimation error square. If you look at this equation, it's pretty simple. E over here is the estimation error after you have the ground truth. And this is the covariance that you get, right? So this is also the error. So it basically means the normalized estimation error square. So this echelon over here, echelon K. So if you have the echelon K and everything is Gaussian, zero mean, and you know exactly the standard deviations, so it actually belongs to a chi-square distribution. And then in this chi-square distribution, you do expectation. That means their degree of freedom. In our case later is 2 for 2D position. So if you have a NES that is very equals to 2, we can say your solution is credible. Okay, solution is credible. That's the most used benchmark today for credibility. Right. So we do simulations. You have the true noise model that your noise is zero mean and standard deviations. And you have nominal noise model, which is the one you use at your estimation. Okay, so you use this as your weighting matrix. And then you do a simple weighted square and you get the claim covariance as this. And we have 3 different scenarios. Underestimated. This is the true model, but our nominee is underestimate the noise. And we have accurate and we have overestimated. So this is 10, but we believe it's even bigger, 50. So in these 3 cases, let's run the NEES, the credibility metric, and see what's the result that we got. So because NEES is epoch-wise solution, so we do average of all the epoch. It becomes average NEES. So you see, we talk about the expectation should be the degree of freedom of chi-square, which is 2 in this case. In the accurate cases, your degree of your NEES is actually 2. It's taking that your solution is credible. But if for underestimated and overestimated case, they are not credible. But this is the quantification value that you can get, like how much uncredible they are. And if you can even using this AEES as a hypothesis test, a goodness of fit. So you can see the p-value. If you're doing hypothesis test, the accuracy is good. But these things only work when everything is Gaussian. So we're using a very interesting data set from Professor Tim Buffer's teams. So it's a UWB data set. So you see it's running at 3 different locations and different locations stop for a while and then walk and walk and walk. This data set is so Starlock. So we're looking at these particular scenarios and we're trying to label if we're using weighted square solution to do this UWB positioning, which area is trustworthy, which area is not trustworthy. So this is the period ID 1 to 6, and this is our label data set. Pessimistic means like you believe your solution is very bad, but it's actually much better. And SMM here means the system model mismatch, meaning like your solution have a bias. So if you look in our just mentioned the credibility metric, you can see it's actually not working that well because in this data set, you have a lot of non-Gaussian happen and a lot of bias happen. So this is really an issue. So what we have to do is that we combining different metric. I don't have time to talk because I'm already taking too much time. So if you're interested, please read our new paper, Credibility, Uncertainty, Quantifications. So we're actually using different metrics and come up with the strategies to tell you how you can really see your solution is credible or not. So our proposed solutions to actually see what is very similar to our label solutions. So no time, but if you're interested, please ask later or in the panel. So this is something that we have been developed. Right, so no time to talk about this. Right, here's our conclusion. So we propose a post-processing pipeline for mobile mapping. Then we using theory to inform our engineering choice. We're still using batch. And we believe multi-layer batch FGO is a good pipeline. And we believe AI assisted device adaptive covariance tuning, the FGO is the solutions to go when you have a lot of data to turn in your noise covariance. And if you want to choose your solutions, which one is good, which one is bad, you need a quantifiable indicator. Please try into using an EES or the other indicator that we propose to see where your solution is good. Yeah, no time. So thank you very much. I'm sorry I'm using too much time. Thank you.
Okay, perfect. Well, thank you so much to the organizers for inviting me to give this talk. Unfortunately, I'm not with you in the what I presume is a nice warm climate of the Gold Coast. I'm here in Toronto where it's like -5 Celsius today. It's really terrible. I wish I was there. Okay, so today I'd like to talk a little bit about radar. You can see some of the robots that we've got with the white dome on the top of all of these robots is a spinning radar. And I'd like to kind of make a case for thinking about radar as a potential sensor for navigating not only in urban environments, but also in off-road environments. Um, but before that, let me just say, I also really like cameras. Cameras have been a big part of my life for a long time. And I just want to show you, a few robots that we have used in the past. Like this robot is navigating using stereo vision. It's driving around perfectly well outside, but it's a nice sunny day. There's lots of good lighting. It's really obvious where all the nice features are for it to navigate with. And I also really like LiDAR. I use LiDAR all the time. It's probably the most common sensor that I use in my lab. This is a lunar rover prototype that's navigating. It's trying to repeat a route using a LiDAR. It's got a previous map of the environment and it's navigating by matching its LiDAR to that map. So LiDAR is also a big part of my life and I really like LiDAR. And, oh, here's another, I like this video. This is another video of the same rover. I'm just showing kind of like, the nice precision you can get when you're using LiDAR to navigate. So there's no GPS involved. By the way, I do really like GPS mainly as a benchmarking tool. I liked everything that was going on in that last talk. Cheaper benchmarking sounds like a great thing to me. I have Inertial Explorer and I also have a Planix Pose Pack, and boy, are those expensive pieces of software. So I hope I don't have to buy them again. Maybe the previous speaker will solve all these problems and produce a nice cheap solution. But you can see the precision with which we can navigate using LiDAR. And here's just one more video, again, navigating using LiDAR. This robot's repeating a route that it was previously taught, and it's using LiDAR, 3D LiDAR, Ouster 128 style LiDAR on this problem. So LiDAR and cameras are great. GPS is great in some situations. And the problem is those things are all great until they aren't great. And what this slide is showing is some real world examples of where using cameras and LiDAR actually fail due to the extreme nature of the environment. So in the top left, we're seeing a robot that's trying to navigate in a straight line. It's actually driving in a straight line. It's being manually driven. And there's a huge snow gust blowing up all around the robot, and the LiDAR is being obscured by this snow gust. And it has enough of an effect on the point cloud that the LiDAR odometry that's being used to estimate the motion here now thinks that the robot is not driving straight anymore. So it completely ruins the navigation. In the top right, so that's snow. In the top right, we've got an example of fog and smoke. So this was work by Kostas Alexis's lab at the Norwegian University of Science and Technology. So he filled a hallway with like a fog machine and tried to fly this drone that had a LiDAR on it. And you can see when there's no smoke, you're getting nice long returns from the LiDAR. But unfortunately, when the hallway starts to fill with smoke, you can see there's an extreme attenuation of the range of the LiDAR. And so this really affects its ability to navigate. And then in the bottom, we've got examples from Martin Magnusson's group at Örebro University in Sweden, where he's deliberately trying to fill the air with water droplets on the left and dust for this indoor sort of mining equipment example on the right. And in both of those examples, the LiDAR and the cameras are highly affected by this particulate matter in the air. So all of these things occur in the real world. And in fact, they occur pretty frequently when you start to actually deploy robots in real world applications, mining, forestry, all these kinds of places. You're going to end up with this stuff happening all the time. And it's a big problem for these sensors. And you might even argue that any sensor with a short enough wavelength is going to be affected by this. So what's the answer? I don't know. I don't know the answer, but maybe part of the answer is that we could switch to using radar. So radar inherently works at a longer wavelength than these optical spectrum devices. And because of that longer wavelength, it can actually see through all of those problem situations on the previous slide without any impact whatsoever. There are lots of different types of radars that you can actually buy for navigation. The ones you find in a typical car. Now you have like adaptive cruise control. Those are typically using radar out on a highway because not only do you get the ability to see through precipitation, you also get nice long range returns from a radar. Again, because of the longer wavelength. And there are many, as I said, many types of radars. The ones that we're working with are these spinning radars, typically from this company Navtech. And you're seeing some data from this spinning imaging radar on the right side of the slide. Hopefully the video looks okay on your side. You can see it looks much like a return maybe from a planar LiDAR, but it's much messier. You see a lot more artifacts in the data. It's not as clean and crisp as you would get from a LiDAR. And so the question is, are the benefits of having a sensor that is inherently robust to all of these environmental conditions, do those benefits outweigh the complications we get with trying to use the radar to actually do something useful? And so a few years ago, we started studying this type of radar and trying to think about, in the context of GPS denied localization and mapping, could a radar like this replace a LiDAR? Could you drive a self-driving car purely based on navigation from a radar like this? And it turns out lots of people are starting to look at radars again. Radar was actually, believe it or not, the very first paper on SLAM was actually using radar data. If you go back to the original paper, the solution to the simultaneous localization mapping problem with Paul Newman as author and others, they were using radar as an example. Anyway, yeah, lots of people trying to look at radar. You can look at the survey paper that we wrote recently that tries to summarize a bunch of the things that are happening in radar. And for those that don't know how radar works, it uses a slightly different ranging principle than a LiDAR. So it's using this idea of frequency modulated continuous wave. And the idea is that you're sending out a chirp that's got an increasing or decreasing frequency. And in the frequency spectrum, that looks like a ramp. And when the signal bounces off the target, it comes back, you get this delayed signal. So it's temporally delayed, but you can also interpret that as a frequency shift. And so if you run an FFT on the return chirp, you can look at that, try to determine that frequency shift, and that will tell you the range. Unfortunately, fortunately and unfortunately, there's also another frequency shift that comes from the Doppler effect. And that's if there's a relative velocity between the target and the transmitter, you'll also get this Doppler frequency shift. And although that might seem problematic because you've got two frequency shifts, how can you tell them apart? Well, the easy answer is you send an up chirp and then you send a down chirp. And so the sign of this frequency shift will change from the up chirp to the down chirp, and this one, the sign will not change. So you end up with two equations and two unknowns. You can solve for both frequency shifts, and therefore you can solve for both the range, but also the radial velocity along that ray, which is quite nice. So we get this extra information inherently from radar. Of course, there are now some LiDARs that also can use the Doppler effect and this type of ranging to produce velocities. But radar's been doing it for a long time, as far back as World War II. Okay, so that's roughly how radar works. We've been trying to build up some capabilities in this area, and as part of that, we've been building data sets and trying to put them out there so that both we and other people can use radar to kind of answer this question of could it replace LiDAR? So one of the data sets that we've been building is the Boreas data set. I think I actually mentioned this last year in the same workshop. Over the last year, we've actually been building up a whole new version called Boreas 2.0, which hasn't been released yet. but there's a bunch more data, similar sensors and the setup on the car, but we're driving in even more extreme scenarios. So you'll see some of those throughout this talk, and that's going to be packaged up as a release of Boreas 2.0 pretty soon. Okay, so getting to the localization and mapping, very roughly, what we tend to do is we take something like radar, we do feature, the typical thing is to do feature extraction, filtering of those extracted features, perhaps registration to a previous frame, or if you're talking about odometry. And then you could also be building up some submaps over time. And then if you've previously stored some submaps, you could be taking the live scan and matching to those submaps if you're talking about a localization problem. So I'm going to talk first a little bit about odometry and then a little bit about localization. So as I said, most people are extracting features from these radar scans, and you can kind of see here's the scan on the left. Here's the example of features from one frame and a subsequent frame being matched. And there's a whole bunch of these different feature detectors. So one of the things we were looking at over the last year is to just sort of do a brute force comparison of all the different feature extractors that people are using with radar. Here's a couple of the examples on the same scan of different feature extractors that are being used. And we kind of looked at, which features are actually the best ones for doing radar odometry. So we did a big comparison of that. That was actually published in this paper. And it turns out that maybe not surprisingly, these common C-fear methods, but also these K-strongest methods ended up being the ones that were the best features for doing odometry pretty reliably across different data sets, actually. So that was one thing that we've been looking at. And then the other thing we've been looking at is to kind of forego extracting features altogether. Because we have this imaging radar, I should actually stop here and say many of the manufacturers of radar don't provide this raw information. What they're doing is they're already extracting features from the raw returns of the radar, and they're just giving you those extracted features. What you really want to do with radar is get to that low-level information. And if you have it, you could actually possibly avoid extracting features altogether. So another paper that we put out in the last year is called Direct Radar Odometry, where we're trying to actually directly match these sort of bird's eye view images that you get from a radar scan, one to the next so that we can do odometry. In fact, what we're doing is we're building up a map over time and then matching back to that. So, but in a sliding window kind of fashion. So it's not really a SLAM solution. It's more like an odometry solution. It turns out we basically destroyed all of the methods that were using features by switching to this direct approach. And so it's basically like a pure optimization play. It's similar to the way that you would try to do a direct method with cameras, right? You're building a cost function that's like the photometric difference on every pixel. But we're doing that now on a bird's eye view radar image. And that actually does amazingly well. So we tried this both in a bunch of test cases on road and also off road, and we beat all of our benchmarks on all of our previous algorithms and most of the other algorithms in the world that use radar. Here's just a couple of examples of that direct radar odometry on the road. These are all on the road. Some long test cases, and we actually went out with our test car, and these are some of the new sequences that'll be part of Boreas 2.0. But we tried to really push the situations where these algorithms tend to fail. So getting out into fairly blank areas, tunnels, skyways, things like that, and just trying to really see if we could break the algorithm. And it did pretty well across all of these things. So even in like a long straight tunnel, all the methods that extract features tend to fail in that situation unless you're using the Doppler velocity. But we were able to, because we're using the direct method, find much more subtle geometry on the side of the tunnel that was enough to kind of zero our error longitudinally down the tunnel. Here are some examples off-road. The off-road performance was slightly less. I should say that we actually do use a gyro with this. So we're combining the radar with a fairly good quality gyro. The gyro is much cheaper than the radar, so that seems pretty reasonable to me. Same thing off-road. The off-road looks a little worse because it was a lower quality gyro. But translationally, the radar does pretty well even in these off-road scenarios. So those are all odometry results. The other thing that we've been doing with odometry is to ask ourselves, well, if we have the velocity information, could we actually just turn that directly into an odometry method? So this is different from the DRO method that I was just talking about, Now we're taking the raw returns. And as I said, you can get both the range and the velocity along those returns. So we're able to get velocities, and then we're able to run ransack on all of the velocities to try to figure out the motion of the vehicle directly. So we're turning the radial velocities into platform velocities, and then just integrating that numerically to do odometry. It's super computationally cheap. Like we can run this in under a millisecond per scan. And it does pretty well. It does also actually require a gyro because the rotational velocities are not observable by the radial velocities of the radar. So all of the translational velocities are observable, so it plays very nicely with using a gyro to get the rotational velocities. But putting that together, you can get a very lightweight odometry method. Here's some of the test cases that we've been building up. So from left to right suburbs all the way through to Skyway. Left is easier, right is harder. Turns out the Skyway was even harder than the tunnel because the tunnel, you at least have returns to the left and the right. And on the Skyway, in some places, you don't really have any returns at all. Plus, there was more traffic on the Skyway than in the tunnel. So those are all places we were testing. And here's just some basic results. When there's lots of features, all methods do pretty well. But in the tunnel and on the Skyway, the method that uses the Doppler velocity, these are the ones that use the Doppler velocity, do match the ground truth, and the ones that don't use the Doppler velocity end up foreshortening the distance traveled pretty easily. So this is making the case for why you would probably want to use this Doppler information from the radar. So now that was all odometry. Switching now to talking a little bit about localization. So we do also build up maps and then try to localize against those maps on subsequent drives. Our best results with LiDAR are pretty much the state of the art, or similar to the state of the art around, that's actually a little bit better than this these days, probably about 4 centimeters of RMSE error. And on the radar, we're approaching that. So remember my initial question of could a radar replace a LiDAR as a localization and mapping sensor? We're getting there, but we're still maybe double the error of what we're seeing with LiDAR. And I think that really just has to do with the resolution of the sensor more than anything. Also, the radar is essentially scanning in 2 dimensions, whereas the LiDAR is a full 3D sensor. We have put all of this together. I work a lot on this like off-road navigation problem called teach and repeat, where you drive through an environment once and then build a map and then localize against it in order to repeat and then close a loop around that. So we've done that a lot with cameras. This video is showing this route following problem with cameras. But at ICRA this year, we also presented the first radar version of teach and repeat. So in this case, the robot was driven through the environment. It built up a sequence of submaps along that using its radar. And then in the repeat mode, it's now fully closed loop, and it's only using the radar plus a gyro to localize itself against those submaps and actually repeat the route. And we did a pretty extensive comparison of this radar teach and repeat versus a LiDAR implementation, which of course is presumably going to do quite a bit better. We got similar results to what we found on the road, actually. So it turns out that the errors were approximately double the sort of like lateral errors, which are sort of our main thing that we're interested in, lateral and heading errors, but mainly the lateral error of the route repeating was approximately double on the radar version compared to the LiDAR version. And again, it's not that surprising because the sensor is a lower resolution sensor. It's seeing less. We're actually a little surprised that we got this to work at all. It was a pretty messy data compared to what you would see from the LiDAR, but amazingly, it's just enough information that you can actually localize reliably. Another thing that we've been thinking about is, can you build maps using one sensor and localize with another sensor? So this was some work where we were flying a drone over our campus and just using a commercial piece of software, building a photorealistic model of the campus, then loading that up in Gazebo and then virtually driving the robot with a joystick to define the route that we would like to actually autonomously repeat. So you can think of it as like zero shot route repeating in a sense, because the UAV flies, but the UGV has never been to this environment before. So we kind of drive it through the environment to find the route that we want to repeat. And then once that's defined, we can extract some localization layer. So we extract the geometry from the photorealistic model, And then in our case, what we do is we extract a bunch of submaps from that larger geometry. So that's how our teach and repeat works, a bunch of these small submaps attached along the route. And here we're doing that both with LiDAR and radar. So you can see submaps being extracted with both sensing modalities. Sorry, this is what the map, if you were to just sort of join all those little submaps together, it would look like this. But at runtime, we can then deploy that onto the robot and it can use those submaps to actually try to repeat, well, not repeat, but drive that route for the first time. And this is what you're seeing in this part of the video. So this is LiDAR. This is just a playback of the data from one of the repeats, and you can see it does match to the maps pretty well. These aren't actually the maps we're using, but we're just showing that the LiDAR data does match to the original mesh pretty well. And there's a bunch of examples. Maybe I'll skip forward a little bit. Somewhere in this video, oh yeah, here's an example of on the left of the robot repeating with radar. This is radar. So you can see in the top right, there's quite a lot of radar. Well, there's radar data and the robot's matching that to the submaps. And that's good enough for us to be able to drive this route. That one's LiDAR. Maybe I'll skip the rest of this video. I don't think there's any more radar stuff in here. I think that's all. The rest is LiDAR. So after looking at all this off-road driving, we can definitely see that there are both easy and challenging conditions for radar. So on the left, we've got pretty easy conditions. There's a lot of man-made geometry in the scene. You can see a tennis court, some fences, and that does pretty well with the radar. In the middle, we've got the sort of scenario we had in our radar teach and repeat experiments, fairly flat ground, but trying to stay away from the man-made structure. And so it's just localizing off the trees and bushes. And then on the right, we've got a more complicated scenario where we're driving through a much more three-dimensional forest road. And you can see the pitching of the robot is causing some interesting artifacts to appear in the radar data because it's really kind of only scanning in 2D, but it's now pitching down and looking at the ground, which causes these sort of shortened ranges. To kind of investigate this further, I may have mentioned this last year actually, but we're building up this big data set driving off-road. This is in partnership with Francois Parmelot's lab at the University of Laval. So we're building up a large multi-season data set that has both radar, but also LiDARs, cameras, and GPS, ground truth. And the hope is that we can try to use this to develop some methods that are more robust to this sort of three-dimensional terrain. So we're not very good at that yet. Here's just a few examples of the data. So cameras in the top row, LiDARs in the middle, radars on the bottom row. And you can see the kind of data that we're seeing. It's an interesting test environment because from summer to winter, there's actually an altitude change of about 2 meters just from the accumulation of the snow. So how many times have you tried to do a localization problem where the altitude of the ground robot changed by 2 meters from the mapping until the repeating? And here's just a video of radar teach and repeat running in this test forest where we're gathering this FOMO data set. You can see the radar map that got built in the bottom right. And there's a few places I'll draw your attention to. So the robot's doing pretty well on this flat ground, even though there's a big altitude change from the mapping to the repeating. But here, as it drives over this pile of snow, you can see it sort of twists left and right, and that's because the localization is starting to fail. The radar is pitching too much, and it's starting to see things that it shouldn't be seeing that aren't in the map, and that causes the localization to get messed up a little bit. So this is pointing to the fact that really we shouldn't be doing this localization in 2D. What we really like to do next is maybe build the model using LiDAR, make the model, the map 3D, and actually use a full 3D model of the radar and how it would actually view the three-dimensional scene and actually localize with the radar in 3D. So that's kind of what we're thinking about doing next. Probably running out of time. We've been deploying this radar on marine robots as well. One of the things that we're trying to do is just localize against Google Earth satellite images. So you're seeing here a preview of that, some preliminary work where we're taking the radar scan. In this case, we are extracting features from the radar scan, and we're matching those features to Google satellite images to try to do localization. Not super accurate, definitely not as good as GPS. And then you might ask, well, it's a good application for GPS. But there's obviously going to be some situations where GPS doesn't always work. So we're just thinking about, how accurately could we localize? I would say not very accurately yet, but maybe there's some improvements we can make still. So I'll try to wrap it up. I'm getting near the end. I've been kind of alluding to the fact that we have some data sets coming. So the FOMO data set is this multi-season one that's on its way. The marine one, we have a data set that we're packaging up right now called Canoe, which is going to have cameras, LiDARs, radars, and post-processed Novatel GPS for ground truth. That should be coming out sometime in 2026. And we're also just about to release the Boreas 2.0 that's got maybe double the amount of data of the original Boreas, a much more challenging situation. So all those suburbs, highway, tunnel, dirt roads with dust, which I didn't talk about, 78 new sequences. So all these data sets should be coming out. They all have radar, LiDAR cameras, and ground truth. That's about all I have to say. I got to do all the talking. Lots of people got to do all the work, and lots of companies got to pay for all the fun stuff. So thank you to all of them. And just one last slide to just say that in July, I took over as the editor-in-chief of the IEEE Transactions on Robotics. I think it's a great venue for some of the stuff that you're talking about in this workshop. So please think about sending us a paper if you've got some real field robotics work where you've been out in the real world and really tested something extensively. It might be a good place for you to send your paper. I think I'll stop there, and if you have any questions, happy to take a quick question.
All right. Yeah, thank you for the introduction. All right, so hello everyone. It's my great pleasure to be here. All right, so since the organizer has introduced me, so I'm not going to introduce her again. So yeah, it's my pleasure to be here, share some of our work on LiDAR and drones. So we combine these two. Well, I got to admit, LiDAR is much simpler. It's much easier to deal with. So my work is much easier than Teams. Well, because the LiDAR sensor itself is rather clean, the data and high quality. Okay, anyway, so before I get into the work, I want to introduce my laboratory a little bit. So our group is called the Mechatronics and Robotic System Lab. So we have a website and we publish our videos, and most of the work we release the codes on GitHub. I want to thank all the students for their great work, who make this presentation possible. And I also want to thank all the funding agencies and also the industrial sponsors who support and not two-man laboratory. So our group has been working on three stream of work. The first is drone design. So it involves a lot of mechatronic system, hardware, embedded system. The second stream is navigation. It's a hardware, software combination. And the third stream is more on the software, the mapping algorithms. So we will go through them one by one. So we have done a lot of work on drone design, but one of the most interesting one, I would I would say it's a POSA. So it's a single actuator drone. But it's able to move in all the three dimensions in the space. So the very interesting part is we only use one actuator, the motor. So there is no second motor, there is no servo, etc. There is only just one motor, but we have to control all the three degree of freedom motions. So the key components we use here is a very special parts on top of the motor, the so-called swashplateness mechanism. This mechanism was initially invented by UPenn. We adopted this mechanism and we combined with an LiDAR sensor. So in this way, we're able to precisely control this single actuator UAV, and it's also able to achieve autonomous flights in unknown environments. So you may wonder why we use only one actuator in this case. Well, we are able to use four, like a quadrotor. Well, the advantages are three. One is a single large propeller has shown much higher efficiency than for small propellers. Well, the fewer motor we are using, the fewer power loss it occurs. So it has a higher efficiency. Well, secondly, as we can see, this one single motor has an unbalanced anti-counter torque. So this will cause the body to have a constant self-rotation. This self-rotation is will cause a sensor to scan all directions in the environment. So as a result, so it's very suitable for scanning, like mapping in unknown environments. So the third advantage lies in the noise. Since a one big propeller, it has a much lower rotation frequency, so the noise it causes is also much more friendly to human ears. Okay, so this work we have continued to improve it. So now we have this POSA 2. So here we have achieved an omnidirectional field of view of the onboard LiDAR sensor. As you can see, we have used a 360-degree field of view LiDAR, but we install it vertically. So the whole UAV with the self-rotation, it's able to sense all the directions. So we have also improved the controller, so it's able to perform rather aggressive maneuvers such as a flip. And we also put a cage around it, so it's more resilient to collisions, either to the static obstacles or dynamic obstacles. So we have also explored a bicopter. Initially, we used servos beneath two motors, but we found that with the servo, the drone has become so the bandwidth that we can achieve is rather limited. So because there is a well-known non-minimal phase effect. So to mitigate this non-minimal phase effect, we have eliminated this servo using the same swatch platedness mechanism. So is a new bicopter design. So there is no more servo motor beneath the motor. Yeah. So as a result, the response time has been shortened yeah, into half of the original one, although it is still slightly larger than quadrotor, but it's quite sufficient for practical use. So it's able to track a three-dimensional trajectory in the space. It's able to resist external disturbances, such as a poke or a wind disturbance. So we have also adopted this design like a tail-seater drone. So conventionally, this bicopter tail-seater drone utilizes the elephant submerged in the downstream of propellers. But this has a limited control authority with the extra moment produced by the swatch platedness mechanism. So the control of such a bicopter tail-seater drone could be much higher accuracy. Okay, so that's a little bit on the design. So the second direction we have been working on is navigation. Especially, we focus on the LiDAR-based navigation on drones. So we started this line of work quite some years ago. So from 2020, at those age, the whole community was still focusing on the visual navigation. So the community was aware of the advantages of using LiDAR for drone, but there is the one big problem which becomes the keener. So that's the weight and cost of conventional LiDAR. So to address this problem, so the first thing we did was to design a new LiDAR sensor that could be more cost effective and more lightweighted. So we proposed a new LiDAR solution based on the Risley prisms. So this solution was later commercialized by DJI and to launch a new brand, the Livox LiDAR. So now the Livox LiDAR has been become probably the largest LiDAR supplier for the robotics community. Well, once the hardware problem is solved, we switch our interests to software. So how can the new LiDAR sensor could enable a new flying capability on drones? So the first topic we explored was how can we achieve a super fast flights with this LiDAR sensor? So we want to ensure safety. We want to ensure collision avoidance, while increase the flight speed as much as possible. So to do so, we adopt a two trajectory strategy initially proposed by MIT. So the faster. So we plan two trajectories. One trajectory is high speed. The other one is safe. Okay, it's guaranteed to be obstacle avoidance. But this two trajectory would take time to compute. So what we done on top of this two trajectory strategy is to implement it purely on point cloud measurements. So in this way, we can avoid the mapping, a volume mapping, like an occupancy grid mapping. So that can save the computation time a grid considerably. And as a result, we're able to achieve extremely high speed obstacle avoidance. So we have done some tests. So the drone is able to fly over 20 meters per second while still ensuring the obstacle avoidance. And it's able to navigate through rather complicated environments, clutter environments, and it's able to avoid a very thin objects like a 2.5 millimeter wires. And the navigation capability is the same at night. It doesn't depend on the lightning condition of the environment. So since the LiDAR measurement is very precise, up to a few centimeters, so this would enable the drone to perceive the environment precisely. So sometimes the drone is cannot fly through like in the horizontal pose, but since due to the high precision environment perception, the drone would be aware it's able to tilt its body to fit to align with the gap. So it's able to fly through the gap by tilting its pose. Well, this one is purely made autonomously based on its onboard computation and sensing. There is no prior knowledge of the shape, the position, or even the existence of the gap. So we have also explored new framework. How can we achieve safe navigation in unknown environments? So conventionally, the community has used a separate planning and control framework. Separate means there is a planner, there is a controller. Planner plan a trajectory like a polynomial, and the controller it tracks the trajectory. But here, what we're doing is we are proposed a integrated planning and control framework. So this is one stage algorithm, but that achieves planning and control at the same time. So this framework we have shown its capability to fly in strong disturbances while being still able to avoid obstacles. And so last year we applied this framework to a actual application. How can we deploy a drone to perform a slope inspection? So the key here is we want to fly the drone under the canopy. So it's not above the canopy where it's quite clear, but we have to fly the drone under the canopy. So this is super difficult because under the canopy, as you can see in the upper right video, so the environment is rather cluttered, and the obstacles like the tree branches, uh, uh, they like the handrails here, and the tree leaves and the safety nets, those objects are super difficult to avoid, to perceive and to avoid. And also the space is rather tight. So our work has also shifted to more physical interaction. So we are able, so for example, we can install a gripper on the bottom of the drone, so enable it to perch. And so in new work, in more recent work, we published in this year, we eliminated this gripper. So the drone is able to perch by its propeller guards. So in this way, we don't have to use any extra mechanism like a gripper. So the propeller guards can naturally serve as a support when the perching. So a third work that's still under review is, how can we utilize interaction, to increase the possibility of a drone in extremely dense vegetation. So the community, the drone community has paying a lot of attention on obstacle avoidance. But in very dense environments, purely avoid the obstacles, often cannot give us a feasible solution because the environment is so dense. If you want to avoid all the obstacles, there is no way to go. So in this case, what we need to do is we have to create a feasible space through the physical interaction, not just passively, avoid the obstacles as it is. So the red video shows, how can the drone is able to, utilize this interaction. So by contact with the environment, it's able to push through the soft obstacles, so that it's able to fly through it. So we also um, incorporate this LiDAR solution with new type of drones, such as here is a tail-seater vertical takeoff and landing drone. So this is has been a very classic configuration in VTOL, a vertical takeoff and landing. But this configuration has a well-known problem. The control is extremely hard because the drone has a wing, but the wing suffer from um, um, this very nonlinear aerodynamic forces. The stalling, right? Because it has to perform a transit during transition, so the angle of attack is very big, and this causes a well-known problem, the stalling, for fixed wing airplanes. So in this work, we have solved some fundamental problem. That's a differential flatness of this type of drone. And so we proved this property, and we utilize this property to design an accurate flight controller. So with this controller, the drone is able to fly through such as a narrow window. Well, in this case, a window and a trajectory is given, before the flight. So what we're doing is testing the control accuracy. So the drone has to track this trajectory very accurately, so that it will not collide with the window. So the upper right video shows the outdoor tests. So the drone is commanded to perform a bunch of aerobatic maneuvers, such as wing over, like a cubanate, vertical eight, a loop, etc. So in most of the maneuvers, the drone required to fly upside down, which is rather challenging. So we solve this control problem. How can we achieve an accurate control? And then we combine it with the LiDAR perception, and we improve the planner. So we developed a new solver that's dedicated to solving this nonlinear optimization problem. The optimization problem coupling this extremely nonlinear aerodynamics. So in this way, the drone is able to plan the trajectory in real time at 5 hertz. So for the first time, this tail sitter, a vertical takeoff and landing drone, it's able to fly autonomously, such as in subterranean, in this parking garage, and in this extremely low altitude field. So the drone has to avoid the trees and all the other objects in the environment. So the capability of the single drone can be uh, uh, scaled up to a swarm of drones. So for the last 3 years, we have been building the underlying localization technique, the odometry for the swarms. So we are particularly interested in decentralized swarm. So we are every component of the drone of the swarm is decentralized from the bottom communication to the state estimation to the control to the planning. So from the bottom up, it's all decentralized. So here shows some representative tests we have done, such as mutual avoidance, navigation through cluttered environment, dynamic teammate joining or leaving, and formation, target tracking, collaborative exploration, and collaborative transportation. So, well, when we first started working on LiDAR, well, many people complain that LiDAR cannot measure velocity, so it's not able to detect the moving object from the static one. So here we put one step forward on this direction. How can we detect dynamic objects from the environments? But we do this even further. So we detect the points on the dynamic objects after the arrival of each single point. So in this way, we're able to detect this dynamic objects at the microsecond interval. This microsecond interval, detection is very similar to the event camera. So we call this work event LiDAR. So because the detection is happening at a rather high frequency. So this video shows some of the tests. So the red dots denote the points on the dynamic objects, while the white dots denote the points on the static objects. So the detection is happening at each point, not on the frame. Well, because the point interval is a few microseconds, so this detection can be very high frequency. So the third direction we have been working on is a mapping, LiDAR mapping. Well, similarly, we started this line of work from 2020, 4 years back. So we have started with the odometry, LiDAR odometry, then LiDAR inertial odometry, and LiDAR inertial visual odometry. So like FastLeo2, so that's a LiDAR inertial odometry we have been working on. And based on FastLeo2, we work on point Leo. So to address the problem of extremely highly dynamic and high speed movements, because we dealt a lot on drones where aerobatic maneuvers, occurred very often. So we want to develop odometry that is able to deal with this highly dynamic motions. So I'm showing the plot. So some of the motion where the inertial measurements has saturated, but even there, the odometry is still able to continue to estimate the true states. Well, LiDAR sensor itself cannot deal with all the situations, so we further incorporate the visual measurements so to combine it into a LiDAR inertial visual odometry. So we lack the extended common filter a lot due to the time efficiency. So here we still use a common filter framework, but we have to optimize a lot on the visual measurements so that it can run in real time without taking much computation resources. So well, odometry inevitably will drift. So a common way to correct this drift is by loop detection. So we have a work, it's called a BTC, binary triangle combined descriptor, to to perform a loop detection. So the key here is we want to develop a the post-invariant um, uh, loop detection methods, because the LiDAR measurement is all three-dimensional, is right. So we want the loop detection is also post-invariant. So we propose a triangle descriptor. So the idea is very simple, right? Because the triangle is a stable shape. That means once we know the length of the three sides, and then the shape is uniquely determined. But for other shapes, polygons, this property does not hold. So we use triangles. So extract key points from the environment, and we form triangles randomly from the key points. And then we match how many triangles are the same triangles from two frames. If the matched triangles exceeds a certain ratio, and then they are taken from the same scenario. So this triangle, as we can expect, is completely post-invariant. So the feature extraction, triangle extraction, and the matching in all this process is completely post-invariant. So we also work on the global optimization, the so-called bundle adjustment for LiDAR scan since the time limit. So I will try to move quickly. So so we have found a very interesting phenomenon for the bundle adjustment for LiDAR when compared with visual bundle adjustments. So we found that we can solve for the feature parameter in the closed loop form. So that this feature parameter can be eliminated from the numerical optimization stage. So this can save the dimension of the optimization problem greatly, because the number of feature is often much, much more than the number of poses. And in our recent work, the work that should be, hopefully that will be published at the end of this year, we are developing a decentralized bundle adjustments. So here we are further decouple the pose coupling, because eliminating the features will steal the optimization problem. The dimension is still the same dimension as the number of poles. Okay, so solving so when the sequence is extremely long, so the number of poles could still be very large. And so solving this large scale matrix, Hessian matrix, would still take much time. So what we're doing here is we want to make it a triangle Hessian matrix. If it's a triangle or block triangle or diagonal, sorry, I want to make a diagonal matrix. So if it's a diagonal or a block diagonal, so this solving this Hessian matrix can be, is only a linear complexity. So we did some theoretical work based on the majorization and minimization framework, and we found that this is indeed possible. And so the Hessian matrix can be a diagonal, block diagonal at least. So the computation on a single device can be rather efficient. And this can also enable us to distribute the computation among different devices. Like we can use like thousands of or hundreds or thousands of small devices, and each device could be the connected device itself. And they can do the computation locally, and they have a way to communicate, to sync, and eventually they're able to solve this large scale bundle adjustment altogether. So our recent work has shown that it's able to process a point cloud data over 70 gigabytes within only 1 minute. So we use 4 devices, device 1, 2, 3, 4, just PC level devices. And each iteration, as we can see here, the blue part is the preparation part. The green part is, the time on each device at each iteration. So we can see that at each iteration, the four devices, they do their corresponding computation. Some is slower, some is faster. And after one iteration, they sync with each other and they go to the next iteration. Okay. So our bundle adjustment also extends to including the visual measurements, the images, what with the LiDAR ready, with the visual measurements bundle adjustment ready. So we can just combine them together. So this way we are able to optimize a multimodality three-dimensional environment. So that's pretty much the work we have done here. Well, since the time is up, I think we can take only short questions if you have.
All right, thanks for the introduction. Well, my name is Zhou from Hunan University, and I have been doing research on vision, have a specific focus on robotic state estimation and multiple view geometry. And this is actually the first time that I present my work at a conference of intelligent vehicles. So it's my honor, and thanks for the invitation. And also I learned that today's workshop focuses on enhancing the safety of intelligent vehicle in a complex urban environment, and also considering my team's research focus is on enhancing to realize the truly high-speed autonomy on the foundation of safety. So I decided to talk about how can we advancing autonomous vehicle with a biologically inspired visual sensor event-based camera. Okay. So in the past 10 years, we have witnessed a rapid growth of mobile robot market, which is driven by the application of smart drones and intelligent vehicles. However, we find their safety are increasingly hard to be guaranteed when their speeds rise. Okay. So this is probably due to the limitation of the mainstream sensing technology, for example, the RGB cameras. And although they serve as the eyes of most mobile robots, their fundamental working principle leads to some performance boundary. For example, when a drone traverses really fast in a forest, the frame-based camera used would suffer from motion blur effect, which would severely degrade the perception and navigation algorithms that rely on image input. And another problem which may occasionally happen in our daily life is this rear-end collision due to a sudden brake of the leading vehicle, right? So, and also the problem is the latency, which comes from the frame-based camera. And and the time interval between successive exposure can be to 50 to even 100 milliseconds, which is a real great deal for timely decision making. Another issue, which also in the context of driving, is this bad imaging quality due to the high dynamic range illumination condition. Right? See the images with overexposure or underexposure, and as a result, any perception algorithm would hardly work this bad imaging results. Okay, so all above mentioned issues have now become a bottleneck to the realization of high-speed autonomy using frame-based cameras alone. When we think about we should investigate and introduce some novel sensing technologies and also develop compatible algorithms on these new sensors. So in this talk, I'm going to share with you how can we solve above mentioned issue with a biologically inspired visual sensor called event-based cam. So what is an event-based cam? Event-based cameras are biologically inspired visual sensors that mimic the transient pathway of our human vision system. So different from a traditional camera that captures the bright information, an event-based camera only responds to the brightness change. Okay, so specifically, every pixel of an event-based camera works independently and asynchronously. And an event is triggered as long as it detects a brightness change. So here, the so-called event is nothing fancy but a data structure that consists of three parts, namely the timestamp and up to microsecond accuracy, and the pixel coordinates by which the event is triggered, plus an additional attribute called polarity, which can be +1 or -1. Yes, +1 or -1, indicating an increase or a decrease of the brightness. So that's a so-called event. And due to this special working principle, it leads to some advanced characteristics. For example, an event-based camera has very high temporal resolution, and also it has a high dynamic range. Also, it comes with low power consumption and a low bandwidth. And here's an animation demonstrating the different working principle between a standard frame-based camera and an event-based camera. Both of them are looking at a spinning plate with black dot on it. So you see, when the plate spins really fast, the frame-based camera would suffer from motion, whereas the event-based camera has no such a problem because of its very high temporal resolution. And if the plate plays normally, okay, so there's no problem about it, it's the standard camera. But if the plate stands still, let's see, stands still, and the frame-based camera would keep captures redundant information, whereas the event-based camera has no outputs because there's no brightness variation. So let's have a look at real data. So on the left is the video recorded using a standard frame-based camera, whereas the right one is the data recorded using event-based one. You can see basically the events are triggered at the textured patterns and pixel and the edges, right? Especially when there's a relative motion with respect to the environment. And if the camera is kept still, there's no events except for some background noises. Okay. So where can it be applied? Actually, we have seen many attempts from different communities. For example, in the field of Internet of Things, we have seen researchers coming up with event-based solution to monitor such an indoor environment with very low power consumption. Okay. And in the field of AR and VR, we have seen our engineers implementing event-based SLAM algorithm to deal with aggressive motion tracking of devices. And recently, I've also seen some astronautic application. For example, in the year 2020, a team from Western Australian University, they made a stereotype, using a pair of event cameras. Okay, astronomical telescope using a pair of event-based cameras to monitor the fast-moving objects orbiting the Earth. And last but not least is some industrial autonomy application where event-based cameras have been used to detect abnormal vibration of a widget or to count those small falling things. Okay, so that's pretty much about the introduction on this novel sensor. So in my team, one of our research focus is to apply event-based vision for scene perception and understanding, dynamic scene perception and understanding. And on one hand, due to this special working principle, especially the high temporal resolution, event-based camera are ideal choice of sensing high dynamic environment. On the other hand, due to their special data format, existing algorithms developed for standard cameras cannot straightforwardly applied. So in essence, in my opinion, the essence of event-based perception is to figure out the way of fitting parametric model on event data. And the challenge here is to answer the following two questions: how to formulate event-based perception algorithm as a geometric model fitting problem, and also how to realize efficient and robust parametric model fitting on this sparse and asynchronous event data. Okay, so in one of our earlier research, we investigate event-based motion segmentation tasks, and specifically, we propose a energy-based multimodal fitting scheme, which iteratively solves two subproblems, namely the motion model fitting and the event cluster labeling. So this algorithm, the result of it is shown here, which demonstrates its effectiveness. It can segment out the background motion and also the independently moving objects from the event data. But the problem of it is that the computational complexity is so high that it cannot be employed. It cannot be applied in real-time robotic tasks. And the reason behind it is that the model fitting algorithm used, which is called motion compensation, which probably one of the most widely employed method, it is so slow. It's so slow, and which leads to a demand for a faster and robust method for model fitting on event-based data. But the challenge is that how can we resolve the non-least squares nature in the problem formulation? Okay, so this is very important problem because in event-based vision, there's actually a lot of requirements. There's a lot of geometric problems that require such a fast and robust pipeline. So to solve this question, in one ECCV paper of last year, we rethink the problem formulation by taking into account the differential working principle of event-based CAM. And we discovered that the event-based normal flow can be actually used as a replicate to the event-based full optical flow vectors to solve a number of geometric model fitting problem, which involves the first order kinematics and the scene geometry. And specifically, we propose a two-step method, which consists of a linear solver and also a continuous time nonlinear solver. And the linear one can lead to deterministic and a closed form solution that can be used to initialize existing nonlinear solvers. And as for the continuous time nonlinear solver, it brings opportunity to deal with sudden motion variation, obviating for the assumption on constant velocity assumption. Okay, and here are some results on a number of geometric model fitting problems. For example, depth estimation, optical flow estimation, and even differential homography estimation, etc. And I think I may not delve into the detailed number. And actually, I think people may feel more interested how this kind of geometric method can be applied in event-based perception tasks. So let's come back to the autonomous driving application. Okay, so and in any autonomous driving system, probably one of the most fundamental functionality is the so-called automatic emergency braking, AEB, right? This functionality may be the most fundamental one. And if you look inside it, you will see that actually the core technique is called time to collision, TTC estimation, which reports the potential time for which reports the remaining time for a potential collision with respect to the leading vehicle. So that's so-called time to collision. And the bottleneck for existing method on using standard frame-based camera is that their updating rate is limited to the frame rate of the standard camera used, which can be 10 to 20 hertz. So considering the nature of TTC estimation using event camera or geometric model fitting one, so we need a much faster pipeline for doing this. And the challenge is how can we overcome the high latency bottleneck of the traditional camera system? And so to do this, we tailored the above mentioned ECCV two-step method in this task. Okay, and we proposed an event-aided time to collision estimation for autonomous driving. And specifically, the contribution of this work consists of a time-varying affine model to describe this the scale change of this leading vehicle on the image plane. And also, the contribution number 2 is a geometric where linear initialization using this normal flow constants. And third one is we refine the result. We refine the linear solution using a nonlinear optimization based on a spatial and temporal registration. Okay. So to evaluate this algorithm, we established a forward collision warning system prototype machine based on the algorithm, and this machine is made up from an event camera and an RGB camera, sharing the same field of view using a beam splitter. Okay, and here's a YOLO V5 module which is running on the input RGB frame, and once the leading vehicle is detected, the event-based TTC estimation is triggered. Okay, so this is a forward collision warning system machine. And yes, we create a lot of high quality synthetic data and also collect some real ones with the help of a local domestic autonomous driving company. And the results looks good, demonstrating the effectiveness of this parametric model fitting based method. However, I think the problem of it is this method employs overly simplified parametric model. And also the experiments are carried out in relatively simple and ideal environment. So this method may not capture the diversity and complexity of real-world autonomous driving scenarios. And also, more importantly, this classical model fitting based method cannot learn data-driven representation, data-driven features, and which prevents them from leveraging the online growing volume of event data to further improve performance and generalization capability. So, however, there's no large-scale event camera data for doing this research, and somehow hindering the development of deep learning-based approach, which typically requires extensive data to achieve robustness. Here are some qualitative results. You can see that this basically demonstrates the effectiveness of our method, even in some challenging illumination conditions. End of this results. This is gonna be a HDR here. The low light condition, which cannot be done by priorly mentioned model-based data. Okay, so this quantitative result also demonstrates the clear superiority of our method against some prior method based on a classical model fitting pipelines. And yes, so that's pretty much about the recent progress from my group. So to conclude, I may bring you with some key insights of this talk and also an exciting pathway to the future work on event-based, event-enhanced autonomous driving. Okay, so recently the low latency, the importance of a low latency perception has been underscored by a industrial test in China. And in this test, we surprisingly find that more than 90% of the existing autonomous driving solution fail in making a timely decision to avoid collision. Okay, this is a serious problem, show a challenge for the next generation of autonomous driving solution. So, and however, as shown in this figure, you can see that there's a trade-off between this latency and the bandwidth, right? Obviously, achieving a higher level autonomy, there comes a cost, right? So we have to make a balance between this latency and the bandwidth. So the question is, can we really establish a low latency and a low memory bandwidth architecture for autonomous driving perception? And the answer is probably yes, because the nature has provided us with a compelling inspiration. In our human vision system, we have two parallel pathway to solve this problem. One is called magnocellular string, which is for the fast motion, and another one is called the powerful cellular string, which is for the detailed texture. Okay. So, and recently this inspiration is actually being transferred into engineering. Some of my previous colleagues at ETH Zurich, they confirm a hybrid design using the sparse asynchronous events with standard frames. Okay. And my teams almost begin this similar research at the same time. And we both believe there are going to be a lot of knowledge transfer opportunities in this direction. And also there's going to be there's a bright future for this direction. So if you feel interested, you are welcome to join. Thank you.
Still morning, isn't it? Oh, morning, guys. And it's really my pleasure to be here and to be invited to give a talk at this workshop. And my talk, I'm going to cover our recently finished cab trial in Australian urban traffic. I'm going to share with you some key learnings, some takeaways from this talk. My name is Shan. I'm a researcher from Australian Centre for Robotics at Sydney Uni. I will start the talk with acknowledgement of the country. And as importantly, I also want to acknowledge the funding source for supporting the research that we're presenting in this presentation. The agenda of my talk is, I'm going to talk about what this cab trial was all about, and then give you some background knowledge about similar trials in Australia, who we collaborated with in this trial, and how we achieved this, what system we used, in this trial, and then share with you the details of the demonstration of use cases, and finally I'll wrap up with some key learnings. What this cab trial was all about. We just recently finished this roughly 2-year-long trial in Australian environment. We just finished this in March this year. And the purpose of this cab trial is to understand the impact considerations, benefits of implementing CITS in Australian urban traffic environment. When we are talking about cab or CV technology, it's not only about the vehicle itself. It's not about how to automate it or how to put the connectivity to the car. It's not only about that. It's also about the infrastructure, how infrastructure can be improved to support this cab technology. For example, what kind of smart sensing technology we need to use for the infrastructure, or how we digitize the traffic light, or what are the safety implications of those CITS technology. So those are all the topics of interest to urban designers, civil engineers, and policymakers like Transport for New South Wales. And speaking of the safety benefit, I think the benefit needs to be demonstrated in particular traffic contexts. So that means the learnings that, lessons we learn from other trials and in other countries will not necessarily translate to Australian traffic environments. So that's why we designed a set of comprehensive demos of CITS use cases in various scenarios on New South Wales roads. And the learnings and the insights we gain from this trial is very valuable to inform cab policy for research community and Transport for New South Wales. Then I want to give you some little bit background about other similar trials in Australia. Of course, this kind of trial is everywhere around the world. Due to the time limit, I only want to cover a few in Australia. Some CV trials in Australia. I want to highlight, for example, CT trial in New South Wales. It's a relatively large scale trial. Involving, like a very hundreds of kilometers in New South Wales, with the smart infrastructure, with freight trucks and passenger cars, and they found a few use cases, including red light warning, intersection collision warning, and hash braking ahead warning, and such and such. But bear in mind that these trials are only talking about connected vehicles. There's no automation, autonomy involved. Next part is AV or cab trials in Australia, and actually for the autonomous shuttles, it's almost there are trials, similar trials in almost every state in Australia. So those are, for example, all-meal shuttles or Easy Mile or Novel, different brands, and they are usually focused on low-speed scenarios in precinct-based environments. And another one I want to highlight is a double smart ute project. So that's focused on the rural and regional areas in Australia. So basically on the picture on the right-hand side, you see, it's a Ford Ranger retrofitted with a bunch of sensors that can do autonomous driving on rural areas up to 90 kilometers per hour. So what's so special about our cab trial? So our cab trial is different because we cover a variety of CITS features. For example, we have two different types of smart infrastructure, including the one from SCADS and another one we developed ourselves. And also we involve two different types of vehicles, cab and CV. And we tested a bunch of CITS messages, including CAM, MAPM, and SPECTRUM, and lastly the CPM, which stands for the collective perception message. I think we are maybe the first trial that uses CPM on a public road environment in Australia. All right, who we collaborate with? So we collaborate with two very important teams within Transport for New South Wales. First one is SCADS. SCADS is a team that they are experts in traffic signal control. They have installed the vast majority of traffic lights in Australia. And globally, they have installed traffic lights in more than that many intersections across that many cities in that many countries. The other team we worked with is a future mobility team. They are looking at future mobility, like future some technologies for the transportation. They own the next world-class testing center, which at Kudal, which is a small town next to Orange. How we achieved the trial? So it basically the trial lasted slightly more than 2 years. We just divided into two phases. The first one, during the first phase, we focused on the development of our vehicle platforms, including cab and CV, and then our intelligent roadside units. And also we work closely with SCADS team to also help them develop their intelligent roadside units. Another big chunk of work we did during the first phase is about the safety assurance. Transport for New South Wales, they have a very well established system for the safety assurance. So this means basically means a bunch of paperwork we need to do, documents where we need to identify any hazards or risks of operating a vehicle autonomously on public roads, and the corresponding safety measures we have implemented to mitigate all these hazards and risks. So as an outcome of this safety assurance, we get the ministerial approval for operating our vehicles on the public road. And then to moving towards the second phase of the trial, it's about the deployment of our intelligent roadside units on public roads, on public intersection. We can't do that ourselves. We are not licensed to do that. So there's a subcontractor of Transport for New South Wales that they did the installation work for us. And after they install it, we fine-tune everything, configure it, make sure that it's all working well. And then when all the technology is ready, the vehicle, the infrastructure, then we again discussed with SCADS to identify a few CITS use cases we're very interested in. And then we did the test in the ACF lab, and then did it in the live traffic, And for something that some particular use case that we can't do it in lab traffic, we did it at FMTRC. Lastly, we wrap up the report in March this year with the final report. What system we used? So first of all, I want to introduce those cabs we developed in our team. Those are electric buggy cars, low speed. It's retrofitted with a bunch of sensors. For example, the main sensor is the Ulster 128 beam LiDAR for both localization and object detection. Then, of course, the GNSS and DSRC for communication and onboard computer. Importantly, it has an in-cabin screen over there for the supervisor. It shows autonomous mode, and also importantly, it's showing the current traffic light, signal phase and timing based on the information broadcast by the smart infrastructure. Yes, this is the route. It's a basic figure 8 route in the Chippendale area near our robotics lab. We are permitted to operate autonomously on following this route. I will give a lot more details about this route later. Basically, localization for the vehicle is based on the graph lane plus lane 2 map. So lane 2 map gives us a lane level information and always also other topology, the connection and the right of way or traffic roads embedded in a map. This is the main intersection. We have the infrastructure installed, and that's a corresponding lane map. Our connected vehicle. It's a standard vehicle. We call it laser car, but our transport for New South Wales partner, they call it Pokemon car. They're more creative than us in naming things. This vehicle actually is not a autonomous vehicle. It already has a bunch of smart sensors, including Novotel localization and the 128 beam LiDAR. But we're not using these sensors for this particular case because this is a connected vehicle. We can't expect all the connected vehicles to have this bunch of sensors there. So that's why we use the minimal sensors set, including just the GNSS. It's even not RTK because RTK wouldn't work in an urban area anyway. And then plus the V2X communication. And importantly, it has this in-cabin screen, as you can see on the right-hand side, to show the alerts to the driver because it's a manually driven car. This is the exciting part of the trial. We designed and developed this intelligent road arena from scratch. On the right-hand side, you see main sensors are LiDARs. Like top, we have 64 beam LiDAR, and at the bottom is an Ulster dome LiDAR, which is a very special LiDAR with 128 degrees of field of view. And it basically can cover everything underneath. So it's good enough to cover the intersection. We have a good coverage of the intersection we have. And yes, we also have a camera there, but camera has issues because it can't work at night and has a privacy issue. So that's why LiDAR is still the preferred sensor modality for road user detection. Behind the sensor head, we see what's inside this control box. It has NVIDIA Orin edge computer, has other network accessories, and everything is self-contained, such that it only needs the power from the grid power. And all the sensor, the LiDAR point clouds are processed locally at this edge computer, and then broadcast to the perceived objects information in the format of CPM using the DSRC device. Here you can see the joint point cloud from these two LiDARs, including the dome one and from the the top one. And with the point cloud, we have a point pillar model for the real-time 3D object detection. Of course, the pre-trained model wouldn't work at all in this case because of the domain shape. First of all, it's a different traffic environment. Second, the sensor, the scanning pattern is very, very different from the sensor, the data that we used for training the model. So that's why in this particular trial, we collected our own data, we label it, and then we train up our point pillar models, and then we deployed it there. And the point pillar is working in real time for object detection, and the results is used to populate CPM, and then it's broadcast to the air using the Coda wireless MK5. This is where the intelligent roadside unit was installed at this corner of this intersection and facing south. But the LiDAR basically can cover everything at this intersection. And let's talk about the other intelligent roadside unit, which is the SCAD smart traffic light. As I said, SCADs, they are the experts for the traffic light control, traffic signal control. Now, the only thing they do is they have the code, a DSRC device that can broadcast they can connect to their back-end control system and broadcast the traffic, like signal phase and timing in the digital version, which is spectrum and MAPM. So our cab can receive this information from their smart traffic light, and then you can see the countdown, which is the timing part of the spectrum message. I want to use this slide to quickly summarize how we integrate all these messages in our cab and CV. So as I mean, we have two types of infrastructure: the SCAD smart traffic light broadcast MAPM and spectrum, while our roadside unit basically has a smart technology that can do the 3D object detection in real time and the broadcast result as CPM. In terms of the users, we have two types of vehicles. In terms of the CV, it has very basic localization, right? They receive this information and then use it in the ADAS features, the driver. While for the cab case, of course, it's more sophisticated. It has LiDAR for very high accuracy localization, and then for the information contained in CPM needs to be transformed into the local vehicle coordinate system before it can be used in the downstream tasks, including path planning and decision making. Yes, we first developed the automated driving technique, and then we need to validate it in our control environment, which is our ACFR robotics lab. So as you can see here, there's no actual intersections in our lab environment. Of course, we have to set up a mock intersection. And then, the traffic light, yes, it's a mock one. It's a toy, it's a very simple intersection. So just to test the logic and test the safety feature that we have. Importantly, we introduced the human in the loop feature to enhance the safety part. Again, cover that more later. And now that's the exciting part, automated driving on public roads. And now I can take a little bit of time to explain what happens here. So this is intersection, unsignalized intersection, which is a roundabout. So here, and then the vehicle comes this way, and then approaching this signalized intersection where we have installed both intelligent roadside units, right? So while the vehicle is waiting here, actually it can talk to the our smart infrastructure about the signal phase and timing, and also about it also can receive the CPM from our intelligent roadside units. And then here you can see the supervisor pressing button to confirm that everything's working well. So that's a safety feature that we introduced, human in the loop, as in the supervisor's job is to assess the environment, making sure that everything is working well. There's no imminent hazard or risk. So then it will confirm that the vehicle is safe to proceed forward to the intersection. And here now it's turning back from here and then going through this signalized traffic intersection again, but turning left to then it will go to the shared zone and come back. So it's basically a figure eight route. Then next part is about the demonstration of CITS use cases. We discussed with SCADs and have identified a few use cases, and here I'm presenting 4 of them. The first one is about red light violation warning. So this is a feature, it's calculating whether or not the vehicle is about to violate a red light based on the information contained in spectrum and the current speed of the vehicle. Kind of similar to time to collision, but now time to it's more like time to whether or not you're going to violate the traffic light. Nevertheless, we can't fully test this feature on public roads because you can't actually fully test it without actually violating a red light. And this is illegal and dangerous to do it on public roads. Instead, we did it at FMTRC. this is a tester check that is just designed for this purpose, right? You can do anything you want there. Here, I'm going to share with you two cases. The first part is, it's a good one. Like this feature external is enabled and the driver is myself. So the warning message, I did the right thing. I stopped in front of intersection. Everyone is safe or happy. And now this is also another feature we say the time to green. So this gives you a prediction like the time remaining until it turns green. So this will prepare me better for the vehicle. Next part is an interesting part. This is a part that we didn't enable this warning feature. So I was like a bad driver. Then I didn't see the traffic light, and I violated traffic light, and then I hit this dummy. That was a lot of fun, but it's a dummy. But in the real world, this can translate to very catastrophic consequences. Next use case we demonstrated is a user turn warning for vulnerable road users. If you're not familiar with Australian traffic rules, I want to explain a little bit. This is an ego vehicle trying to turn right to this alleyway, and in between there's a pedestrian crossing. So according to Australian rule, I want to move this way a little bit. Okay, that's good enough. That's good enough. So there's just a light for the pedestrians. If it's red, that means the pedestrians are not allowed to cross the road, so the vehicle can safe to turn. But when it's green, it depends. When there are pedestrians are allowed to cross the road. If they are crossing, then they have the right of way, so the vehicle needs to give way to them. But if there's actually no one crossing, then you still can turn, right? So this information is contained within the spectrum. So that means in this use case, actually, this information is now brought to the screen here. So when this one crossing is green, you can see very soon this warning turns on to give the driver a warning that, watch out, the user turn warning is activated. And it's a very user-friendly way to remind the drivers that you need to pay attention to this information. But in the reality, how do we know actually someone is crossing the road or not? So then here's how, the CPM can be very useful. Don't forget, we have our intelligent roadside unit installed here, monitoring the whole intersection 24/7. So this sensor is actually telling the ego vehicle whether or not someone is crossing the road. As you can see, someone is actually crossing the road, and this information is picked up by our intelligent roadside unit and broadcasted to the vehicle through a CPM. So you see this extra line underneath saying pedestrian detected. So that's a real-time detection information from the smart infrastructure. And again, it's an informed way to tell the driver that you need to pay special attention to this particular case. And yes, we also did other extra demonstration of use case. For example, we did something related to cooperative driving. For example, again, Australian traffic rules, when you are interacting with the roundabout, let's say you're coming this way, you need to give way to any coming traffic from the right-hand side. For the CAF, it can be done using the onboard sensors, right? For, sensing any traffic coming from right-hand side. But now, because these are all connected vehicles, they are exchanging cam. So this means this can relax the dependency on using the onboard sensors for the detection of any incoming message, because basically this car is sending out the cam. Sorry, this car coming this way is sending out the cam to tell the ego vehicle that I'm here, so you need to give way to me. All right, finally, I want to wrap up. There are a few key learnings. Firstly, through this CAF trial, we've demonstrated the actually important roles of the smart infrastructure, providing local perception extension and improving the reliability and safety. And it also gives us a lot of learning about, what are the infrastructure requirements for supporting, CAF or CVs, for example. What's the right sense modality what's the right way of training up a machine learning model for object detection, and how we can integrate the spectrum map message in the decision making and path planning, for example, and the safety assurance process. This is I only briefly mentioned about this, but actually it's worth another 1 hour of presentation. But maybe it's for a different day. And yes, human in the loop. This feature, I think, it really is helpful, as in adding an extra layer of protection for the safety. And lastly, I also want to highlight the key roles of SCAS and FMTRC, because they are not any technical team. They are not any research team. They are just the government agencies in this area. So working with them really gives us a lot of, learnings, as in thinking out of the box instead of just the focus on the technology itself. It helps us, gain the higher level or more holistic view on the whole technology. So I want to give special thanks to that. All right. So last one is, if you want to know more, please feel free to follow us or check out our webpage. We have a bunch of other very interesting projects in our in our team. So feel free. So that's all for my presentation. Any questions?
Thank you for the kind introduction. That was a lot of detail. Thank you. Okay. I apologize that I can't be there in person. I had already traveled abroad earlier, and unfortunately my teaching requirements prevent me from coming to Australia right now. But yeah, thank you for the kind invitation. I'll be talking about this safety performance trade-off. So first, let me show you this exact same vehicle that Mal was showing. And here's our collaboration with Sydney Uni back when I was at Michigan, where we're making formal safety guarantees and the vehicle is autonomously driving through Eastern Avenue, I believe. So the cool part, this is me in the vehicle. So I had some skin in the game, so to speak. And I'll explain in this talk how we're making this formal safety guarantee. We've also done this in other dynamic environments. So here is a little quadrotor drone avoiding some pedestrians and autonomously making some decisions to basically ensure collision avoidance. And I think traditionally what you would see is that in these settings, you always have some trade-off, right? And the point of this talk is really to just dive into that trade-off and understand it more deeply. So first, let's talk a little bit about safety. Imagine I'm trying to get my autonomous car down the road to the global goal, so perhaps this green star, and I create some intermediate waypoint. I can always plan, so ideally you can plan to get to the little waypoint, but when you track it, if you have some high fidelity model of your vehicle, often the dynamics are not perfectly matched to your simplified model. However, if you can compensate for the error between these two things, and this may be also incorporating some sensor uncertainty or localization error, if you can compensate for those errors cleverly, you can avoid all of the obstacles and get down the road. So in this talk, I'll focus on the simplest type of safety. What is the trade-off we have to pay just to get collision avoidance, but with a 100% guarantee? And that 100% guarantee, I want to emphasize, is to prove it theoretically on the whiteboard, but also to create the correct numerical techniques to transition that onto a real robot. I'll talk about 3 ways that we've done this. So on the left, I'll introduce reachability-based trajectory design, which we actually designed in collaboration with the folks at the ACFR, and then some recent progress on integrating neural network models into this type of reachability analysis. All right, so let's dive into RTD a little bit. Let's consider this safe motion planning problem. We want to minimize some arbitrary costs subject to our dynamics and not hitting anything. You may think of various ways to solve this. You can solve it at the highest level, maybe with RRT or A-star, trying to factor in your dynamics. And one way to think about this is also with the state lattice method that's more focused perhaps on the dynamics of the vehicle. And the reason I introduced this is just to give you the idea of if you have a parameterized space of trajectories that you could track, you can plan in that space. If you find obstacles, you can use that to cancel out certain parameters, but you always pay this trade-off directly of how much you dilate your obstacle, which can eliminate some possible trajectory options. And that trade-off is what we'll talk about more today. A different way to enforce safety is at the lowest level at the tracking controller, where you treat everything above it as basically a disturbance. And CBF, or control barrier function, is a common way to do this. So imagine that I have some nominal trajectory and I don't want to hit this car. If I can pre-specify a subset of my state space that is safe, this green box, the CBF idea is to turn this into a quadratic program constraint that adjusts your nominal control to stay safe. However, there you again pay this trade-off where, depending on the size and shape of the forward invariant set or control invariant set that you're trying to enforce, you may have more or less control options available. So what we developed is this reachability-based trajectory design method that plays this trade-off, to the best of our knowledge, pretty efficiently, more efficiently than many other alternatives. We begin with a forward reachable set computation. So taking the same parameterized trajectory idea where points in this parameter space K correspond to trajectories. And if I took all of those trajectories plus the fact that I can't track them perfectly, this is the object that I'll call the forward reachable set. You may also hear it called a forward reachable tube. And what you're seeing here are two projections of a high dimensional object that lives in the parameter space and the state space of your robot or your autonomous car. We can compute this object offline and then at runtime use it by basically intersecting with obstacles in the state space or workspace and projecting that into the parameter space. So identifying all of the unsafe trajectories. And then given a waypoint, we can create a cost function and optimize over it to find a safe and basically collision avoiding path, despite the fact that we have some tracking error in our system. The nice part is if we can do this fast enough, as our vehicle moves through the world, basically we just rinse and repeat. We create obstacles, map them into our planning space, create a cost function and optimize over it, and the resulting tube around our trajectory is safe. And we can repeat this perhaps every t-plan seconds, for example. And we have to, previously we had to specify this planning rate offline. Now we've, in various contexts, gotten this down to, running at 40 hertz or 50 hertz. So we can do this replanning really quickly. But throughout this talk, we're thinking more like 2 to 4 hertz is really the rate I'll be talking about. In the ideal circumstance, we can redo this procedure, rinse and repeat over and over and over, and eventually get to our global goal. Now, the original version of this talk had a bunch of mathematical proofs and things in it, but I've omitted that information just to get to the cool ideas. But I want to emphasize that anytime you see a cartoon in my talks, it's backed up by rigorous math, and there's code available on GitHub. Okay, so what does this look like? Again, now you understand what this green object is that the robot is computing in the top left corner. Here we're doing localization and mapping with LiDAR. And if I play the video again, you'll see the robot is autonomously making some lane change decisions. However, you do see perhaps some conservativeness. The robot has some idea that it may leave the road, for example, because the reachable set is slightly bulging out of the road. It may use the shoulder due to that dynamics and localization error. In this particular case, it didn't, but we had the same exact thing going on here in this EV vehicle, EV video at Sydney Uni. And you can see the robot recomputing its reachable set over and over and over. In this case, the algorithm was running at 4 hertz, I think, or 2 hertz. So I emphasize this as a motion planning algorithm, meaning it does not need to run super fast. 10 hertz in practice is probably good, and 2 hertz is great for research code. As a fun thing, we also created a bunch of random environments with pedestrians, and we can make a mathematical proof as well of avoiding pedestrians modulo correctly predicting their behavior. In this place, compared to a sampling-based or state lattice-based method, we can complete more tasks, but often in this case, because we are making a mathematical proof, we do trade off a little bit of performance. In this case, we actually went faster, but if you look at a more structured scenario, so here we had some unprotected left turns, very similar to what Dr. Shan just showed. So we were simulating this setup exactly, and I'm so glad to see that the folks at Sydney Uni have put it on the actual vehicle. In this case, we were able to complete 99 out of 100 left turns, where one of them we basically stopped. We never decided it was safe to cross the intersection. And the key idea here was, like, compared to a model predictive controller with some heuristics to decide when to turn left, we can formally guarantee that we know exactly when it's safe to turn across traffic. you have to excuse me. This is a left turn across traffic, which should be flipped to be a right turn across traffic in Australia. But the idea is that we can use this formal logic to decide when to be more patient. And as a fun thing that we've done more recently, a year or two ago, so we're applying a very similar algorithm here to have a digit humanoid walk through a crowd of people. And it's autonomously making decisions with a reachable set analysis to avoid these very brave grad students who volunteered to be obstacles. I think I have here's a video. Let me skip.
We present our work on socially.
So we have some hardware experiments here, and I hope the video is playing clearly. Is it laggy over there, or is it okay? Okay, I guess I can't really hear you guys in the room, but in the bottom right, you can see the robot is recomputing its reachable set, the reachable set of the pedestrians and its own, while also maintaining balance. And then the gantry is just there for safety of the pedestrians in case the robot trips and falls. Okay, so now that we have this idea, we can do very powerful things with this concept of parameterizing trajectories and integrating uncertainty. So here's a recent basically two works from ICRA this year and RSS the previous year on piecewise affine reachability computation. So thinking about a different way to represent the uncertainty in our system. Let's go back to this problem, but let's make it more exciting. So suppose I'm driving down the road and I want to park in this parking spot where I'm the blue car. The best way to do this, obviously, is to drift completely laterally, lose traction, and slide into the parking space. This is an obviously unsafe thing. It takes a human driver years and years of practice to be able to do this reliably, and you still crash all the time. So our question to answer was, how can we get a robot car to do this with no crashes? One way to think about this is to represent the dynamics as a piecewise affine system, where we can decompose its state space into polytopic regions, and in each region, you can think of it as having an affine flow, so linear plus offset. In cartoon form, this is just a bunch of arrows, but please understand it's a little bit more subtle than that. But I think the cartoons should be sufficiently illustrative. All right, so if we take this, we can in fact exactly represent a ReLU feed-forward neural network as a piecewise affine system and vice versa. Actually doing the conversion between these is a little bit tricky, but the cool part is now what we can do is directly learn our dynamics with the neural network, and then because of the piecewise affine analysis, we can start making safety guarantees through that type of linear logic. Imagine that we have some goal set that we want to reach. The way we actually did this with this park method was to take a nominal, like a candidate trajectory, and think about which regions it touched in which order. So here, if I have some example trajectory, it may pass through these regions from left to right. There are existing methods from my colleagues at Stanford who showed how to compute backwards reachable sets through these sequences of regions. And we took this to the extreme of computing basically all possible safe trajectories that'll reach the goal. Here, for example, is the associated reachable set with uncertainty of one trajectory being shown. But the cool part is we can do this basically iteratively. So we take our goal region and we take one backwards reachable set and do this over and over and over to under approximate basically the set of all trajectories that will reach the goal. Okay. So that's what this might look like, this blob of a whole bunch of trajectories that, and remember, these are like drifting trajectories of a vehicle completely laterally sliding. So we actually have to use data to generate these trajectories in the first place, which was literally me driving the little RC car around. Because we're reasoning over tubes of trajectories, we can actually directly apply the same method for obstacles. So in this case, our parked cars, to compute the backwards avoid set of each parked vehicle, and then subtract that from our backwards reachable set. So we get this backwards reach avoid set where we provably over approximate the avoid sets and under approximate the reachable set to guarantee that we've correctly approximated the set of trajectories plus error that can reach the goal without collision. Okay, so that's the key idea. And just to tie it to the RTD concept, I've only been showing the workspace projection of these reachable sets, but in fact, we're again reasoning over parameterized trajectories where K here represents the parameterized space. So before we dive into the drifting car, let's think about what it means to parameterize that space. And here, this is an example from the control barrier function literature where you want to control a planar quadrotor to go between two obstacles and reach a goal region. One option is just to take the full system and somehow parameterize trajectories for it. And another option is to, in a lower dimensional sense, take a very common parameterization for quadrotors, which is minimum jerk polynomials that are basically close enough to the dynamics that if you treat these polynomials plus error, you will you have to compensate for the error, but you'll do a good job of planning. And we found that taking the full system dynamics ends up being way too conservative in this case, which is maybe a little bit counterintuitive. Often when you have the full system, you would think you're reasoning over it, so it's much less conservative. But in this case, because of the difficulty of parameterizing trajectories for the full dynamics, ends up being more conservative. Whereas with the polynomial trajectories, so this reachable set is the blue region here, it's a much larger region from which the robot is able to reach the goal safely. So the point of this is like thinking carefully about the way you construct your space of possible motion plans. And I hope this sounds obvious, but like thinking carefully about that really does matter when implementing these provable safety methods. The other key thing we want to understand is, well, so think about the simplest possible example of flying through a narrow gap where you just want to fly straight through a narrow gap that's a little bit wider than your robot. We compare it against a classical Hamilton-Jacobi method called fast track, and then a recent neural control Lyapunov barrier function method. And we found that both of these methods, first of all, do not have a numerical correctness guarantee. So they can theoretically prove that something is correct about their collision avoidance, but when you put it on the robot, there's a gap in the way you code these implementations. The other key idea was that if you treat your higher level parts of the autonomy stack, if you treat your high level planner and your trajectory planner as adversarial, your robot ends up being so conservative that it cannot fly through a gap. In the worst case scenario, not only is it more conservative, but you also then fit a neural network to it in the neural CBF case, and your robot just flies through the wall. So these are some of the key points that we overcame by thinking about this piecewise affine reachability. And of course, I have correctly flipped these animations around so that the roads reflect Australia. But we did a bunch of simulations to make sure that it works with this drift parking, with neural dynamics. And here we're seeing multiple evaluations where there's multiple types of tracking error causing the vehicle to drift to different parts of the track. But the nice part is because we have a guarantee on finding all possible trajectories, we discovered that this initial, what you're seeing here is the initial condition set from which the vehicle has to begin to safely complete this maneuver. This tiny green triangle here, if you can see my cursor. The cool part is we're able to find that object, but it's very, very tiny. Like this is a very hard problem to solve to find the set of all possible trajectories that could drift safely into this parking spot. This was encouraging in simulation, and so we did it on hardware, where this is with motion capture to get the state of the vehicle. But the nice part is we did this 15 times and had 0 crashes, where 15 was about the number we could do before the battery ran out, and they kicked us out of the motion capture room. This is very satisfying because we went all the way from proving something on the board, carrying it all the way through to showing that it works on the real robot. Now, we haven't had anybody brave enough to donate their car to let us sit in it and try this in a parking lot, but hopefully that's coming soon. And if you know someone who has a car that we can drift, that'll be really fun. Okay, so I want to tell one final little story, and this one's a little bit quicker than the other two, that thinks about basically previously we had safety, then we had safety and then performance, and now can we think about putting safety and performance together at the same time? Okay, hopefully some of y'all have seen these recent imitation learning methods where basically you teleoperate a robot a whole bunch of times to collect a data set, and then you can roll that out, and it enables manipulator arms especially is the hot topic right now, but imitation learning can enable robots to do things like manipulating soft objects or fluids much more reliably than model-based methods. So these model-free methods are quite impactful. However, in very simple settings, for example, you can see there are April tags here on all of these obstacles. In these very simple settings, just rolling these policies out naively cause very odd failures where they just crash into stuff, even objects that they've been trained to avoid. So again, I asked the question that the simplest type of safety, if we enforce it, how much performance do we have to give up in these novel types of policies. I'll switch to a navigation example, so a maze navigation example. Here, consider for example, a diffusion policy, and you might think of it as reasoning over the flow. This is why it's diffusion, is the flow of a distribution over trajectories. And if you do this correctly, you can navigate from start to goal in these mazes if you've trained on maze-like data. However, as soon as the maze changes, for example, thickening the walls, you will immediately start having violations where in this case, a very simple model of a robot crashes into the walls. This is exactly where model-based thinking, control barrier functions, model-based controllers come in. You can also think about this as reasoning over a distribution of trajectories, where it's shifting the distribution according to a dynamical model, in this case, also subject to some constraints, for example, collision avoidance. Okay, so these two things are now coexisting, but how do we actually formally get them to work together? One way to think about this is as a joint process. The previous parts of this talk that you've seen are basically to do a performance check first and then a safety check. So do the blue optimization and then the yellow optimization. And this almost always leads to suboptimal but safe generation of motion plans for your robot. So what this looks like in practice is that if you have safety enforcement post hoc after your learned policy, you end up intervening or the safety layer and the policy fight each other over and over and over. In this case, again, the safety layer is actually this RTD style of thinking that we were talking about earlier. And then the policy is, in this case, a diffusion policy. So instead, what we do is, hopefully the visual makes it very clear, but we just optimize over both of these things at the same time. And we can get to much better solutions. So here, what you'll see for the little ball tracing through the maze is that it only gets maybe 2 interventions over the course of the entire thing, and it travels much faster. I want to emphasize here that the safety guarantee is the exact same. The only thing that we've done differently is optimize for safety and performance simultaneously through a diffusion process. Okay, and then we put it on a manipulator. It still takes a little bit of time to do this on a manipulator, so we had to show this at 3x speed, but we've recently gotten to work a lot faster. So keep an eye out for that in the near future. Okay, so that's the end of my talk. I think I'm on time, maybe a little early. What I want you all to take away from this is that we can get both safety and performance with some careful engineering. If we're thoughtful about the way we write things down on the board, what proofs we make, and we're thoughtful about the way we convert that into a numerical implementation on the real robot, we can actually not make as large of a compromise as you might initially think. Okay, I'll leave this slide up, but I'd love to take any questions if anybody has any. Thank you.